Hi everyone, we are back and let's go into our exam 2 practice exam. So let's look at some of these solutions. So let's take a peek at the snapshot below. Red is the average particle size. So if we're looking at 3D particle growth, we should know, and we have our good old expression to see which particles grow, which particles shrink. So we have dA dt equals minus 2c naught times d times v bar squared times gamma over RTA times 1 over a minus 1 over a bar. Oops, 1 over a bar. So if a is greater than a bar, so this is let me write a little bit nicer here, but we ran out of room just at the end there. 1 over a bar, our average particle size. So if a is greater than a bar, so 1 over 100, that's going to be minus, so, versus 1 over 10. So then I have my dA slash dt is greater than 0. If a is less than a bar, dA dt is less than 0. Kind of makes sense. Why? If I know that my chemical potential of a sphere is equal to chemical potential not of an infinite plate plus 2 gamma v bar over r. So 1 over r, if I have and I flow from high chemical potential to low chemical potential, if I have a large radius, small chemical potential, so I'm going to go from high chemical potential to low chemical potential. So these big guys, everything larger, are going to grow, and then a check mark, these particles are going to shrink. That's it. What particle size will grow or shrink the fastest? Basically, we see that the maximum growth rate will be a is equal to 2a bar. So if you take that derivative of this function here, you'll get that value. So we have answered that question. Write out the chemical potential for the orangish, yellowish, and then the purple one, which atoms will. So again, we already wrote out chemical potential. Oops, let me write that a little bit nicer. My chemical potential of a sphere is equal to mu naught of an infinite plate plus 2 v bar gamma over r. So I know that my chemical potential of my, we'll call this yellow, is greater than my chemical potential of my, purple here. So I know that they're going to flow from yellow to purple because, again, high chemical potential, low chemical potential. Let's see where to indicate this. So I know I'm going to flow from basically yellow to purple. Yellow to purple, shorter jump, and we got it there. Excellent. Look at the plot, log base 10, not natural, of the average 3D particle size of what is the slope of each curve. So we know that our average particle size scales as t to the 1/3, and then in front of this we have kind of this function with a bunch of constants. But at the end of the day, the thing that we are focused on is basically this prefactor in front of it that is d, basically d over t. So again, we could change temperature, and we know that d is equal to d naught times exponential minus q8 over kt. So we have this exponential term with temperature that's going to beat out that 1 over t temperature there. So what is the question actually asking me to do? So we found the slope, it's 1/3, because if I do this equation, so if a bar is proportional to basically d, some other constants as well, d over t times, t to the 1/3. So if I do the natural log of a bar proportional to log of d over t plus 1/3 log of time. So I know that the slope will be 1/3 because right here, and then this will be my y-intercept. So as I increase, basically as I go up here, temperature is increasing as well. So that's my y-intercept. So I'm specific with that. And let's see what else. And we found out what's the, use your equations. We've done all of what we wanted to. Now we can move on basically to part D. So if I'm nucleating these particles from a liquid solution, what free energy terms pushes me to nucleate a solid? Which free energy term pushes me to stay in liquid? So when I'm nucleating a particle, delta GR equals minus 4/3 pi r cubed delta GV plus 4 pi r squared gamma SL, where delta GV is equal to delta HF delta T over Tm. So the term that pushes us to form a solid is always our volumetric term. The creating surface area does not want us, that makes me want to stay a liquid. I don't want to nucleate particles. That's the only thing holding me back. So my undergraduates measure free energy for nucleation as function particle radius. On the blue curve indicate the critical radii. So that's right here, my R star. What radii will grow? So basically, if I'm on this is going to grow. This was going to shrink, because why? Well, because as I go down, if I go from here to here, I'm decreasing my free energy. If I go from here to here, so if I go from 1 to 2, I'm increasing my free energy. If I go from 1 to 2 here, I'm decreasing my free energy, so my particles will want to grow there. Based on free energy consideration changes. What is happening with the other curves? Well, my other curve, that red curve, I'm shifting. So remember, my R star is basically proportional to 1 over delta T. So I believe, if you take that, that's my critical radii. So if I decrease my amount of undercooling, I'm going to shift this R star here. So that's what's happening on the red curve. The green curve here, that is heterogeneous. Excellent. Shifting, what can be causes? Yeah, perfect. Yeah, and that's it. That's a nice one. So again, similar to what we've seen on the problem set, similar to kind of what's on the other videos or the other problems. So, all right, now let's go ahead and get to number 2 and look at equation 66 in our notes. All right, see you in the next video. Thanks, bye.